All right, folks, I just want to welcome you back to Unit 10. This is Thermochemistry. We've looked last time at the transfer of energy or transfer of heat from one object to another, and we used this formula. We said that Q is equal to M times C times delta T. In other words, mass times specific heat times the change in temperature, and that was final minus initial, by the way, is going to tell us how much heat is being transferred. So if we look, for example, at a container of water, and the water has in it some metal, then heat is being, say for example, the metal is warmer than the water, heat is being transferred from the metal into the water, right? So the metal is cooling down and the water was heating up, and we could measure that change in energy. But what do we mean by temperature? So we want to define temperature now, okay? So the particles of matter are in constant, rapid, random motion. What do we mean by that? Well, let's take a tank. Let's say that that tank is full of gas. Let's say it's nitrogen gas. Well, those particles are moving around. Let me just draw a few particles here. I won't do too many. But those particles are moving around rapidly and randomly. And by the way, as they hit the sides of the container, we'll learn in our gases unit later on that they're creating a pressure, right? So they're moving all over the place. They're colliding into the walls of the container. They're colliding into each other. But the important thing is that they're moving at a certain speed. So they have an average velocity. Later on, when you take statistics, you will learn about something called a normal curve. This is a normal curve right here. What it means is that right in the middle, most of the particles, the area under the curve constitutes the number of particles. Right in the middle is the average velocity. Now, that's not to say that there are not a few particles that are moving very fast and some that are moving quite slow. So these are fast moving particles and these are slow, right? Just like that. But the average is right in the middle. So temperature is dependent on the average kinetic energy of these particles. The higher the temperature gets, the faster the particles move and the faster the average kinetic energy. Likewise, the greater the energy of the particles, the greater the temperature, right? So temperature is really a manifestation of kinetic energy. The greater the kinetic energy, the greater the movement. The greater the movement, the greater the temperature. Now, next year, you'll learn that kinetic energy has this formula. 1/2 the mass times the velocity squared. So you can measure, actually calculate the kinetic energy of these particles if you know their mass and you know their velocity. But we'll talk about that next year. All right, so let's take a look then at a couple of definitions. You may already know these, and so that's all right. We just need to review them. They are exothermic and endothermic. Exo and endothermic reactions. Now, reactions can be classified as to whether they release energy into or absorb energy from the environment. Reactions which release energy are called exothermic. Okay, so this prefix exo tells us that energy is being released. It's going out. If you have an ex-boyfriend, where is he? He's gone. He's out, right? So exo means out, thermo means heat, so heat out of the reaction. And the reaction container will often feel hot or warm since energy is being released. Endothermic reactions feel cold since they are absorbing energy from the environment. So endo means heat coming in to what we call the system, right? So let's just say, for example, that I had a beaker and I have some kind of a reaction going on in the beaker, and I can, if I touch the beaker with my fingers, I can feel heat being released from the beaker into my hand. We called that exothermic, right? Exothermic. But on the other hand, endothermic reactions take energy from the environment and they move them into what we call the system. In other words, energy is absorbed by the chemical reactions. Some of you may be athletes. Those of you who unfortunately might have suffered injuries, maybe a shoulder injury or a knee injury. Sometimes what will happen is the trainer will go out and they have this bag and they'll break the bag, and what's going to happen is when they break the bag, there's a chemical reaction inside which is endothermic, and the bag gets very cold. They put it on your shoulder, they put it on your knee or whatever you've injured, and it will make it feel better because the cold is absorbing heat from your hand or your shoulder or whatever it is into the bag. All right, so it feels cold. All right, so let's talk a little bit about now something called enthalpy. What do we mean by enthalpy? Well, the formula for enthalpy is H. Enthalpy, think of enthalpy as the heat contained within the bonds of molecules. So if I have, for example, a molecule, I'll draw this right over here, say methane. Methane is CH4, so we have carbon with 4 hydrogens attached to it. Within those bonds, within each of those 4 bonds is energy. And we can take that energy and convert it into heat for cooking or whatever it is that we need to do by a process that we'll talk about in just a few moments. But the point is this: inside of these bonds is energy. So delta H is used to denote whether a reaction is endothermic or exothermic. A positive delta H for a reaction means that the reaction is endothermic. So endothermic, positive. Heat is absorbed from the environment, so the reaction vessel, such as the test tube or the beaker, is cool or cold to the touch. So again, positive delta H, endothermic. Negative delta H is exothermic. Okay, a negative delta H is exothermic. So a negative delta H for a reaction means that the reaction is exothermic. Negative delta H, exothermic. Heat is released into the environment. So the reaction vessel is warm to the touch or hot to the touch. Okay? By the way, delta H is the enthalpy of the products minus the enthalpy of the reactants. In other words, the heat contained in the bonds of the products minus the heat contained in the bonds of the reactants. There's always products minus reactants. All right. So you may have seen these potential energy diagrams before. For the endothermic process, the products have a higher energy than the reactants. In other words, delta H is positive. So here we have an endothermic reaction. So this one's endothermic, right? Meaning that the reactants have a lower potential energy than the products. A lower potential energy than the products. So in order to go from reactants to products, we have to kind of go uphill, don't we? We have to go up, and then we end up with a higher energy products than we had reactants. That's endothermic. Now for exothermic reactions, we have just the opposite. For an endothermic reaction, we do have to go up temporarily, and we'll talk about that little bump right there in just a moment. But eventually we fall back down, so the products have a lower potential energy than the reactants. Okay, a lower potential energy than the reactants. Now I want to talk about this energy right here, going from reactants to the highest part. That's called the energy of activation. Now, for all reactions, both endothermic and exothermic, it requires that we use something called, that we attain something called the transition state. And what we mean by that is, we mean that there's this kind of unstable intermediate between the reactants and the products. And we call it, it's at the very tip or very top of the curve, and we call that the activated complex. So it's an unstable intermediate between reactants and products. But in order to form products, we have to go through the activated complex. In other words, we have to form this unstable compound in order to achieve the products. So the difference in energy between the reactants and the products is going to be called the energy of activation, or abbreviated E sub A. So E sub A is the energy of activation. It's the energy required to achieve the activated complex. Now, as you can see, for an endothermic reaction over here, that energy of activation is going to be quite large. All right? It's going to be very, very large. But for an exothermic reaction, even though it's there, it's not going to be as large. So this is an exothermic reaction then. Exothermic, where the energy of activation is not quite so great. Okay, now let's talk a little bit about delta H. Delta H is the relationship in energy, in terms of energy, between the reactants and the products. For an endothermic reaction, the delta H, remember, is positive because it's products minus reactants. High number minus low number, positive. But for an exothermic reaction, it's going to be negative. It's products minus reactants, so low number minus high number, delta H will be negative for an exothermic reaction. By the way, while we're on the subject of these potential energy diagrams, let's just mention briefly catalysts and how they work. A catalyst works by lowering the energy of activation. So if you want to make a reaction go faster, one way to do it is to just give an altered pathway. So let me just change colors of pen here so I can show you. Well, let me try. Let me see. There we go. We'll do this color right here. And if you just do this, if you can provide an alternate, I don't know if you can see that very well, but if you can provide an alternate pathway that doesn't require such a high energy of activation, then you can make the reaction go faster, and we'll call those catalysts. So again, catalysts increase the rate of reaction by decreasing the activation energy. Okay, by decreasing the activation energy. All right, let's go on to the next one. Let's take a look at some real numbers here. So here again are two potential energy diagrams, right? So this one on top is exothermic because products have a lower potential energy than do reactants. C and D have a lower potential energy than do A and B. So that's exothermic. As opposed to endothermic, where the products have a higher potential energy than does the reactants, right? Now, let's take a look at some numbers. We've got potential energy of reactants, 40 kilojoules. Potential reaction of products, only 20 kilojoules. The energy of activation, difference between high to the very highest point to the reactants is 100 minus 40, 60 kilojoules of heat for the energy of activation, right? You must provide 60 kilojoules of heat in order for this reaction to go. And so the delta H then is this distance right here. This is delta H. So delta H is going to be the difference between products and reactants. Products is 20, reactants is 40, 20 minus 40. Negative 20 would be the delta H for this reaction. Let's look at this bottom diagram now. We've got, this is an endothermic reaction. The potential energy of the products is, reactants, is 20, right here on the 20. The potential energy of the products is 40, right there, right? Potential energy of the products is 40. What's the energy of activation? Well, we're going to have to go from 20 all the way to 70. So 70 minus 20, 50 kilojoules is the energy of activation, right? From 70 to 20 is the energy of activation. What would the delta H be? Remember, it's products minus reactants. So 40 minus 20 is 20 kilojoules of heat is the delta H. So this would be the delta H for this reaction, right? I drew that arrow just a little bit too long. Let me shorten that just a bit. If I can, let's see. There we go. And I need a pen. There we go. From here to here, let's say, right? So that's my delta H for this reaction. All right, so now we know the difference between endothermic and exothermic reactions. The diagram shown on the top is the exothermic reaction, and energy is being released. It's being released. Therefore, the potential energy of the products is lower than that of the reactants. Folks, that'll do it for this one. I'll see you on the next one. Thanks. Bye-bye.